So let us continue with our electrochemistry. Okay, right. In order for electrochemical reactions to be into effect, or for electrochemical reactions to occur, there must be a constant flow of electrons across the interface. That's the one of the driving forces for electrochemical reactions to occur. So in a system, there actually has to be electron donors and they actually have to be electron acceptors. Okay. So if these are in a system, let's say they are both present at a same interface, okay, then there is there's the same interface with an electron conduction through the substrate and ion conduction in the electrolyte. We can say that we can confirm that this is an internally short circuit. Why? Because there is no useful work that can be extracted from the same system, because as the electrons are being donated, the electrons are being accepted because they are present at the same interface. Okay, so examples of such systems are actually in your corrosion of metals and actually in your leaching. This is all. These are some of the systems that can be termed to be, when you define them in terms of electrochemistry, you can term them to be internally short-circuited. Now, these systems now can be manipulated when you change the concentration of the species. You can actually manipulate the system. When you change the temperature, you can actually manipulate the system. Or even the introduction of further species that contribute as electron acceptors or electron donors. This all affects or manipulates the way electrochemistry, the way electrochemical reactions will proceed. Right. However, if the interfaces are spatially and electrically connected, it becomes possible, sort of like now, to extract some energy from such a system. So it also becomes possible to manipulate the reaction at the interface by actually applying a certain potential to them. Why? Because there's a spatial or electrical separation between your donor and your acceptor of electrons. Okay, so examples of these systems are actually used, for example, when you're charging your battery or electrowinning processes, okay, or your cathodic protection of a corrodic metal. Those are all examples of a system which is not short-circuited. Okay, and you can now manipulate by this can be manipulated by the application of a potential. Okay. Right. So this is an example or a depiction of an electrochemical cell. Consider on your left here the anodic side on your left, and consider on the right here the cathodic side. Okay. So in this electrochemical cell at the anodic side, okay, you have got your dissolution of your metal here. Okay. So your M is being oxidized to metal ions and releasing a certain number of electrons. And then at your cathodic side, okay, your metal ions is actually being reduced to your metal in solid state. Okay, so what actually is happening here? At the anodic side, as you can see, there is production of your metal ions. Okay, that is happening at your anodic side. And when these metal ions have been produced, okay, because there is a mass transfer, you can see that there is a change in here in the morphology, which means that there was something here. So there is a mass transfer now of your metal solid to your metal ions. Okay, so your metal ions actually being produced and actually getting into solution. This is what is happening at the anodic side. If we now take a look at the cathodic side, we can see now that here our metal ions are actually being consumed, okay, actually being consumed to form an S here. So here probably there should be something to show that there is some deposition here, and the Mn Mn2 plus, that the Mn ions that are produced at the anodic side are actually being consumed at the cathodic side. So you can see now this is the ion flow, okay? And inside this component here, at the anodic side, we are producing some electrons. So these electrons are being transferred here to the cathodic side, where your electrons are being consumed for them to allow the deposition of your metal. Okay. So this is an example of an electrochemical cell and what happens in the electrochemical reactions. Okay. So, as we said before, leaching can actually be termed as an electrochemical reaction. That's why we are studying the thermodynamics of electrochemistry, and that is why we are studying it after we have done some leaching, because leaching itself can actually be termed an electrochemical process. Why? Because there's actually some redox reactions that are also happening. There can also be some electronation or de-electronation that is actually happening. Okay. So we say electrochemical reactions involve the transfer of charge over some finite distance through electron and ion conducting substances between spatially separated cathodic and anodic side. Okay, right. So because there is no charge accumulation, we can conclude that the rate of charge released at the anode, okay, must be equal to the rate of the charge that is consumed at the cathode. Okay, if there is no charge accumulation, then your anodic currents must be the same or equal to the ones that are being consumed at the cathodic side, cathodic currents. Okay. So what is the driving force for electrochemical reactions? From your history, I think from your previous studies, you understand what delta G is and what is E cell is. So your delta G is your Gibbs free energy, and your E cell is the potential of the cell. Okay. So these are the driving force for your electrochemical reaction. So when your delta G, your Gibbs free energy, is actually less than 0, then we can say that this reaction is bound to occur. Then we can say if E cell, the potential of the cell, is actually greater than 0, we can say that this electrochemical reaction can actually proceed. Okay, right. Let's consider the dissolution of copper in aerated acidic conditions. So we've got here your cathodic reaction that's happening here, and it has got an E cell of 1.229 volts, which is your standard hydrogen electrode potential. Okay. Then you've got at the anodic side, that is where this is the copper reduction. If you're moving to the right, it's your copper reduction. If you're moving to the left, copper the leaching. That's here. So the E cell for this one is 0.34 compared to the standard hydrogen electrode potential. So this now is the overall reaction, okay, for dissolution of copper. So you find that your E cell for this reaction now, for this overall reaction, will be the E cathode minus the E anode. So your E cathode 1.229, your E anode 0.34. So your E cell for this reaction is actually 0.89. Okay. So from this cell, we can see that this one is definitely greater than 0. So we can say that this reaction can occur spontaneously, or it is favorable to occur because we've got what, a positive cell potential of this reaction. That's the driving force of electrochemical reactions. Okay, right. So let's do a simple recap, assessing the feasibility of using the equilibrium constant or your solubility product. Assume you've got this kind of reaction. Okay, that's your reaction, which is this is a compound, and then you dissolve it. It forms into maybe it's a salt. It forms into separate cation and anion. The KSP, or the solubility product of this reaction, can be termed to be the activity or the concentration of these ions. Okay, then we can actually depict that. We can predict precipitation. Okay, precipitation um, if this value is actually greater than the standard KSP, we can predict the precipitation. We can also predict some dissolution if the product of these is actually less than your standard KSP for that particular reaction. So this again is also an important part we see when you are seeing. It's also an important part when you're talking about your solubility, and you're talking about your activity, and you're talking about the spontaneity of your reactions. Either they can be dissolved, or either they can be leached, or either they can be cemented or precipitated. Okay, right. Let's consider a reaction as shown here. Okay, your A, B, C, D with molars in small letters. Okay, so for any arbitrary conditions, this is the formula that gives you your Gibbs, the change in Gibbs free energy of a reaction. Okay, so what is delta GR? Delta GR is the free energy, the Gibbs free energy of a certain reaction. And what is delta G naught? This is the standard Gibbs free energy for a reaction. So it's a standard. That one is it's set, and we know. Then definitely your R becomes your gas constant, your T your temperature, usually in Kelvin. And then your K is your reaction quotient. Okay, I'm sure you understand what your reaction quotient. If we are talking about this reaction here, your reaction quotient will be the activity, activity of product number C to the power small c, okay, times the activity of product D and to the power molar or small d, then over the product of your reactants, okay, over um, the, 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 the multiplication of the constant of the activity of your reactants here. So activity of A, product A, to the power of your molar small a, times the activity of product B times to the power molar or small letter b in this case. Okay, so what is activity? Activity is given here, um, is given as shown in this reaction here, where your gamma is called the activity coefficient. So usually for your dilute solutions, the gamma is generally equals to 1. Okay, remember I told you, why do we use activity and not concentration? I hope you have answered that question. Yeah, okay. So let's consider, for example, this kind of reaction. Okay, how do we calculate the Gibbs free energy for this reaction? So for this reaction here, the Gibbs free energy will be for this reaction will be the Gibbs free energy of formation of Cu2 plus, and also Gibbs free energy of formation of your H2 plus. These are your products. Okay, minus the delta G formation of your reactants. Okay, so what are our reactants? Our reactants are CuO and your H plus. So here we say for this one, for copper it's 65.9, then for water minus 237, and for CuO minus 129, and then for this one it's an ion minus 0. Okay, then the delta Gibbs free energy for this reaction is actually 41.94 kilograms per mole. Okay, all right. Now, as we say that in electrochemical reactions, there is movement of charge. So in an electrochemical reaction, a charge which is measured by the number of electrons or the number of charge carriers, okay, times the charge of each carrier must actually be moved through a potential difference E to change the reactants into products, for which the energy difference is given then must be equal to delta Gibbs free energy minus the number of your charge carriers minus the Faraday constant and times your the potential. Okay, so let's define this again. In an electrochemical reaction, the charge, okay, so your charge is NF, and you said N is the number of charge carriers, might be your electrons, times F, your charge constant, and then E, the potential. So the charge must be moved through a certain potential for the reaction to occur, for your reactants to be changed into products. Then the energy difference must be equal to the change in Gibbs free energy. That hence this reaction here, that delta G is equals to negative NFE. Okay, so if we make now the potential subject of the formula, we can now say that E is equals to delta change in delta Gibbs free energy over NF. Okay, now um, you realize that when you're talking of electrochemical reactions, it is actually more convenient to use you see potential and for your reactions, as it can be readily measured and generally more understood in electrochemical circuits. It can be measured, it can be altered in electrochemical circuits much more easily than the delta Gibbs free energy. Hence, you will see that all our reactions, all our diagrams, your Pobe diagrams, they will not be in the form of Gibbs free energy. They will be in the form of potential and your pH, of course. Okay. Now, there are some deviations that can occur from standard conditions. Okay. So given that change in Gibbs free energy is equal to the standard Gibbs free energy plus your RT ln K. Now, for standard conditions, okay, all activities, okay, that's word again, and all fugacities. I also want you to study what is fugacity, what's activity, and what fugacity. These are equals to 1, okay. So if your activities and fugacities are equals to 1, it means that your K is generally equals to 1, and your ln K must be 0. And therefore, delta G is equals to the standard Gibbs free energy. Okay, so your Gibbs free energy relative to your reference must be equals to 0 if we are using a standard hydrogen electrode potential system. Okay, if you are using that for your electrochemical systems, your relative your Gibbs free energy relative to the standard or the reference electrode must be equals to 0 when you're using your She. What is She? Is the standard hydrogen electrode potential. Okay, so the potential or the value of a half cell for any concentration of species can be considered to be to indicate the free energy of electrons in that system, of course, relative to the reference system. So you find that you consistently meet this reference system, reference system, reference system. Why? Because there are several types of reference systems. But in our case, we are going to be using our reference systems, which is She. Okay, so what is She? Your standard hydrogen electrode potential. That's the one that we are comparing the potential. That's the one that you're comparing every change to. That's the standard, which is that's the, the, the foundation or the basis and the yardstick for every change in potential that we are measuring. We are using the hydrogen as a standard. Okay, right. So it means that the alternatively you can say now your potential is equals to the potential of the standard hydrogen electrode. Okay, so the equilibrium concentration of species would actually indicate the tendency of for a reaction relative to that of the standard state. So you're simply saying this potential, whatever potential, the cell of whatever we are comparing to, it's equal to that of the hydrogen electrode, standard hydrogen electrode potential. Okay, so we are comparing the tendency of a reaction relative to that delta G is equals to NFE in our previous slides, and therefore we can come up with what is now called the Nernst equation, whereby your potential can now be given with this formula. Okay, so this formula is called the Nernst equation. Formula is now called the. So the Nernst equation is used to describe deviations from standard conditions for electrochemical systems. So this is the formula for your Nernst equation. So your E naught are potentials. This is your standard hydrogen electric potential, let's say. Your R is the gas constant, your T, your temperature, F, your charge, and then N, number of charge carriers in the electrons, and K is your reaction coefficient. So if you, because you know the values of your R, you know the values of your RF, you can actually change, or you can actually make your reaction from this one, and it becomes the one on the right. These are the same reactions. Okay, the same equations. Sorry. Okay. Right. So this is a quiz that just you should do as you are doing these slides. Okay. Given that delta G is equals to this, I want you to prove and show how E is relates to E naught. Okay, I want you to prove, I want you to show that E is equals to that. Then I also want you to prove that this reaction is equals to this. Okay, then also, I'm sure you already maybe found out why. I want you to what is the difference between activity and concentration, and which one is preferred and why. Then also, I want you to add what is fugacity. Also define what is fugacity. Okay, so this is your quiz that I want you to just to do as you are doing your notes and as you are writing down your notes and understanding the lectures. Okay. Right. So we've been talking about the standard hydrogen electrode potential for quite some time. What is this hydrogen potential? What is this standard? So we say that half cell potentials of other cells are measured relative to that of the standard hydrogen electrode. Okay. Okay. So this standard hydrogen electrode is as a potential of 0 at 25 degrees Celsius. Okay, so by implication, so delta G formation of H plus is 0, of H2 is also 0, and then the P of H2 is actually 1 atmosphere. This is at 25 degrees Celsius, and that's why it is a reference. That's why it is a reference as a reference electrode to all the other potentials or the other half cells that can actually occur. Okay, so here we can also see that the Gibbs free energy is 0, and also the E is 0. Okay, for the standard hydrogen electrode potential. So you can, that's why, for example, you can see here that your copper 2 plus 2 electrons is given as 0.3 volts. Then there is a She at the end here. So it is this She which is saying we are comparing whatever here we have to the standard hydrogen electrode potential. Okay,